Hello, hello. Am I audible, sir?
Yeah, you are audible and am I audible?
Yes, sir. Yes, sir. You also audible. So, good afternoon, everyone. Today is the second session of five-day FDP program on next generation technologies in electronics and computer science, trends and teaching approaches. So, all of the participants are requested to please make silent. So, before I just uh, starting our session, we are just give you some brief description about our session. For this session, we have session speaker Dr. Subhajit Das sir. Dr. Subhajit Das sir is a senior member IEEE, senior member ASR, IEIC Japan, IETE, ACM, life member of IAENG. He has obtained his PhD in VLSI Interconnect Modeling from the School of VLSI Technology at the Indian Institute of Engineering and Science and Technology, basically IST Shibpur, in 2019. His professional journey began at Wipro Technologies, where he worked in embedded systems (PES) before transiting to academia. As a part of innovative development-based research, Dr. Das made significant contribution to the DST-funded SMDP C2SD project under the Digital India program initiated by the Government of India. Additionally, he collaborated with Purdue University, USA, and Hiroshima University, Japan, as a part of SPARC project from 2018 to 2020. Currently, Dr. Dasher serves as an associate professor and convener of the Center of Excellence in Advanced Low Power VLSI and COE Nanotechnology at the University of Engineering and Management, Kolkata. Basically, it is UEMK. As well as he is visiting a professor of IC Design and Fabrication Center, Jadavpur University. He is active present member of the IEEE Kolkata section newsletter committee. He has previously served as an associate professor at SR University Warangal and as a staff researcher at the HISIM Research Center, Hiroshima University, Japan. With over 16 years of combined experience spanning industry, research, and academia in VLSI design, embedded system, and digital signal processing, Dr. Das has an impressive record of accomplishment. He has published over 100 peer-reviewed articles in prestigious journal books, patents, and conference proceedings. As a frequent reviewer of high-impact journals such as Journals of Computational Electronics, Pinjar, IEEE Transaction on VLSI, and IEEE Transaction on Device and Materials Reliability, Dr. Das also contributes significantly to the academic community, and his research interests include nano interconnect modeling, the design and compact modeling of high power electronic devices, semiconductor memory design, Internet of Things, recognizable embedded systems, and advanced signal processing techniques in VLSI design. So, Dr. Subhajit Das sir, you are welcomed in our 5DP FDP program.
Thank you very much. Thank you for your nice and elaborated introduction. So thing is that I would like to give some kind of my experience along with the present research and the next research thing that may be helpful for all the faculties, and maybe the few faculty could collaborate with our team. So let's start my presentation, and firstly I would like to sure could you please give me the access of sharing?
Sir, I just now sir give you the permission. Okay.
Yeah. So my presentation is visible for everyone now.
Yes, sir, it is visible.
Yeah, just a minute. Let me kind of make the. So since your this FDP's theme is next generation technology in electronics and computer science, trends and teaching approach. So thing is that here I will be mostly touching the embedded system and VLSI. So itself the embedded system and VLSI is a multidisciplinary. So kind of electronics is there, a big amount of computer science is there. So I think in the next few years, VLSI and embedded system will be the part of our journey. So my theme of this talk is VLSI design and nanoelectronics for future intelligence system. I would like to thank Professor Gopal Jana for giving me this opportunity to talk in this Department of Electronics and Communication Engineering, Department of GKCEM, and also IET. So this is a smart era. Smart era means everything is getting smart except us. So basically, we are making smart and becoming more like dependent on smart thing. However, this is the time where we will make the system and everything smart. So, like to start with, I will just share you one small thing. Whenever I was in Japan. So let's see that how smart was there uh, the corresponding waiter. So waiter is number of when the number of people are getting smaller, and so you are trying to be use the smart system. So this is a kind of smart machine. Just a minute. So this is a smart era. So if we are telling that what is the smartness is coming from, and how this smart thing are we can implement, we are implementing. Mostly the electronics, computer science, and mechanical people are doing the job. So thing is that smart means basically before the smart, what was there? We previously learned about the semi-automatic and automatic, right? So semi-automatic and automatic, what was there whenever something was controlled. Like if I can give you the example of washing machine. The washing machine previously we have to do like set the corresponding value of water level, give the corresponding water level to open, and gradually the corresponding water is to fill the corresponding drum. Then it come automatic whenever just you have to choose the values that what are the things you want to do and what will be the maximum kg, and automatically the amount of water will come depending upon your choice. And now when the smart washing machine comes, then no need to give you the corresponding weight or type of material, whatever you are putting inside the washing machine. They are basically getting that what is the weight, what is the type of cloth you have given, what is the kind of mud it has. Accordingly, it will start doing his washing. And similar thing for AC. AC means here the corresponding now the smart AC can judge that what is the size of the room and how is the corresponding humidity, how is the temperature. Accordingly, it will adjust the temperature and cool the system. So whenever this smart, automatic, and all these things are coming, definitely it is telling that okay, fine, that everything is smart means it is able to see. Like we have the eye, ear, skin and all these things, so that we can judge the corresponding system inside us. So same thing we are incorporating inside a system so that it can sense all those things. And accordingly, we used to write the program, and the corresponding system is doing its job. So what the thing is coming here, that is the sense or sensor. So now I'll just give you one small thing, that whatever the project we are doing, I'll be starting with the drone itself, that we are want to get the biofarming. Biofarming means the pest repellent, whatever the pesticide has been used, you already know the previously the DDT, whatever has been used, that was the poisonous effect was stayed for only 10 years. 10 years means whenever you are taking the food, DDT going inside your body, and it stayed for 10 years and then it goes away. But whatever the pesticide now we are using, so they are 10 to the power 5 times they used to stay. So in our lifetime, it will not go. And basically, that is the reason, one of the very big reason for this cancer and all these bad diseases. So that's why we started the biopest repellent. So it's like, thing is that here we thought that okay, let do something. Basically, if you Japanese researcher are doing this job, so we have already collaborated with them. So they are doing in their way, we are doing in our way. The thing is that we will just send a ultrasonic frequency. Ultrasonic frequency, so that the pest they are there in the field, they will just go away. So thing is that since this ultrasonic frequency is non-hearable, non-unaudible for the human being, so it will not affect the human being, but that is audible to specific pest. So that's the research we are doing, that is going on in Japan also, that which pest don't survive in which frequency. And basically this frequency we are using and made the corresponding pest compelled to move further away so that they can't stay in this section. And the basically the pest nature is, if that is go away from there and stay somewhere, it will not go back, come back after 3 months. However, to do that, we have tried to do that with the help of drone. So drone means, so you already know about the, basically we tried to do the swarm drone. Swarm drone is now very popular after this Pakistan attack and everything. So basically swarm drone we have used, so it will be small and we can use number of drones so that they are cost friendly also. So it can just do the things for the long number, a huge number of area. So we use the Arduino, or further we have used the various other microcontrollers to make the corresponding transducer array which are emitting the corresponding frequency, ultrasonic frequencies. Now the challenges comes, and I will tell you that what are the challenges we faced and what is the role of VLSI over here. So whenever we want to employ this pest repellent frequency, the pest repellent frequency, we can use the corresponding transducer array they used to throw the frequency. But this frequency's magnitude, that is the power of that frequency, should be very high. Whenever we want to make more powerful ultrasonic frequency, then we require some power MOSFET. So thing is that getting multidisciplinary gradually. So it was starting with drone, then those all there we are doing the all this programming, embedded programming and everything. Gradually it is coming the sensor. Then it is the communication part. That is, the communication means we are basically making the corresponding signal, that frequency signal, and sending the frequency signal, ultrasonic frequency signal. Now it's coming the power amplifier. Mostly power amplifier is a section of electronics and electrical part. But the challenge here, this is a swarm drone. So swarm drone, if anybody knows that one, just I would like to show this laser pointer. So this is a swarm drone. You can see the what is the size. And if you know about the power amplifier, this power amplifier is little bit bigger in size. So we can't accommodate a power amplifier and or in this kind of drone. So we need to make it smaller to accommodate. So this corresponding thing, whatever I told that we need to do, need to make a gate driver module, which is basically driving the MOSFET and creating the power signal. This power signal basically giving the high power, emitting the high power ultrasonic frequency. But here the big problem I told, the swarm drone, lesser size, and another one is heat. I will come into the heat point later on. So let's see how this bigger thing to make it smaller, basically that is the purpose of VLSI. So VLSI is very large scale integration. So if you told like what is VLSI, very large scale integration, so it's a big name. So in the name itself, the VLSI thing is there. So for the sake of area, I am telling you that for the sake of area, we need to make smaller. Smaller, not only smaller, we need more and more features. Like in your mobile phone, previously the mobile phone was a similar size. But gradually, whenever the mobile is getting upgraded, lots of sensors and its circuit has been incorporated. So make these sensors and circuits incorporated in the similar area, we need to make it small. So that's like the sumo is there taking some space. If I want this space, number of sumo, so we make the sumo slimmer. Simple. The same. So more number of components will be integrated, very large scale integration. So no, more, a very large number of component will be integrated and placed in that position. So in a single previous area, and this area is mostly same, but number of component had increased. So that is the scaled integration. So scale integration, after that is come that firstly that is SSI, small scale integration, then large scale, then ultra large scale, and now the giga scale is coming. So that's why this Moore's law, Moore's basically the corresponding employee of Intel. So whatever, he's a kind of game changer in the VLSI field. He started given a target to Intel that every 2 years, the number of transistor will be doubled in a single area. Same area, the number of transistor will be double. So basically that trend is coming from 1965. Now it is 2025. And in 2025, when AI came into the picture, then the things getting faster. Rather, now the synopsis and few I will show you Samsung, they are telling by using the AI, we will make this 2 year to 1.5 years, rather 1 year. So getting smaller every day by day. Whatever I told, the integration. So now you can see the accelerometer. Whenever we are running or we are walking, it basically counting your speed, counting your step, gyroscope, electronic compass, pressure sensor, various filters, duplexers, RF switches, MEMS micro mirror for camera sensor, and this all these things are there in your mobile phone. So lots of thing has been integrated in a single system to make this fabulous VLSI system with a huge big features. So that is VLSI. Now, what I told is what is the future of VLSI. Now, after coming, whenever this AI came, the Samsung told that we are doing the 3 nanometer process. So get a little bit idea about 3 nanometer or micrometer. So basically, micrometer is nothing but the width of our hair. The corresponding hair width is 1 micrometer. So 1 micrometer into 10 to the power minus 3. So if you can split, it is 1000 times your hair's width. That become 1 nanometer. So one single transistor is having this will be taking this amount of space. So 3 nanometer, you can understand that in a small area how many transistor could accommodate. Okay, Samsung is moving towards, like it's telling that they will make it 1 nanometer production. And now 1 nanometer is basically bigger. Now the Armstrongs are coming. So you can understand the growth of VLSI and how the more and more features are coming. Now the corresponding Facebook has already told the next is this mobile, the next is your spectacle. No need of mobile. Mobile will be obsoleted within next 5 years. And the spectacle will come which will do actually more and more things than this present mobile. So you can understand that how the VLSI will evolve, and I am very happy to understand since I'm a part of SMDP National Semiconductor Mission. So this VLSI and embedded systems the future in India is getting bigger and bigger. So now already we have the SCL, that is it was Tower Semiconductor. Now it became SCL. SCL is a part of DRDO. So we have the Fab Lab of SCL. They have started their journey to 45 nanometer process, and I am sure by next 2 years it will come to 16 nanometer and 9 nanometer process. So it's getting better. Now Apple is coming. Micron already came. We went to Japan last year in the Micron's Hiroshima's fabrication lab. So basically the Micron Hiroshima lab is now splitting, and they will be doing the assemble level job in Ahmedabad, Silicon City. So now the VLSI is supposed to come in every BTech syllabus. And gradually BTech already, in BTech, you have already found that lots of institutions have started BTech in VLSI, because it is told by next 5 years, approximately 50,000 skilled professionals will be required per year in the VLSI field. So I told this is the transformation from that Nokia 3315 to our Apple iOS that 16.16 series already came. So this was I told about the transistors. Now another thing we used to miss, that is the interconnect. Interconnect means the wires. Basically the wires we are using inside the chip. That is the most big headache for everyone. Now Apple has made something they didn't even disclose, that they had prepared a fabulous interconnect that is taking lesser space, as well as the corresponding loss is less. So what is the corresponding interconnects thing? Thing is that you can make the corresponding transistor smaller. It's fine. But at the same time, you have to decrease the width of the interconnect with the wire, which is basically passing the current from one transistor to another transistor, from one system to another system, from power to the devices, the modules. So thing is that then what is the problem? We can make the width smaller, smaller, and more smaller. But what is the problem? I am just telling you. The problem became the capacity to flow the current. So you need to flow the current in a smaller area. If we think basically those who are working in VLSI field, we actually think everything with the water system, our reservoir and water system. So thing is that current we are thinking that is the kind of water that is flowing. The water flowing in a singular, in a particular per unit time, that is basically electron flowing per unit time. So that's requires some area. So if the area is squeezed, like previously, you can see this is a bigger pipe. So bigger pipe can flow a huge amount of water. But whenever the pipe becomes smaller, then the corresponding speed become higher, and accordingly you can find that if the corresponding pipe is not that rugged, not that strong, the pipe will be just busted. The similar thing is happening in the VLSI circuit. When we are decreasing the width of the interconnect, what is basically happening? It is happening like the huge amount of electron try to flow through this corresponding smaller area, and a huge amount of heat is generated, and the corresponding wire is burned. That is called electromigration. So everywhere we are in search of a good material, mostly superconductive material, which has the power of carrying huge amount of electron in a particular time, per unit time basically. So my PhD work was based on the graphene nanoribbon and carbon nanotube interconnect modeling part. So graphene nanoribbon and carbon nanotube, this kind of interconnects are the future of the VLSI system. And whatever I told, that it is told like whether because Apple didn't yet publish or told that what is the interconnect they are using. But the thing is that mostly it is supposed that they are using carbon nanotube interconnect in the new iOS, the Apple systems. So that's why they were able to just do this thing. Somebody is using something so that these things are coming. Could you please check? Uh, just a minute. Why these things are coming? Let me just close this. Is this visible now?
Yes, sir.
Yeah. So now I will be telling that I will told that what is the source of heat. I told that was the interconnect. Now I am coming back to the previous thing that where the power amplifier was required. Okay. So this power amplifier, what is there? Our problem I told in last slide, last previous this that we are using the gate driver module, right? So gate driver module to make this power amplifier so and emit the corresponding frequency, ultrasonic frequency. Okay, but the problem was there since we are using the corresponding drone, swarm drones. Just a minute. This swarm drone is there. So swarm drone, we need to make it smaller, and as well as we will face the challenge with area and heat. So how, let's check how the heat has been like got the, we have already asked this, already published this in published the corresponding patent and patented this our solution. So I'm just sharing this solution to get an idea, give the idea, so all the teachers, those who are working in VLSI, embedded system, power electronics field, so that they can work in this field, because this area, the work area is very scratch, and people are actually in the verge of getting all these things. So let's start this one, that this is the corresponding power amplifier. Sorry, this is the GPIS tag I'm telling. So I am just giving a corresponding GPIS thing, so that the gate driver, there is a GPIS, general purpose inverter stack is there. So where we can find that basically this gate driver is told about is told as GDR. So GDR means whenever we are giving the corresponding through GDR, we are making this transistor on at a time. So this will give the rising edge, okay, and this will, the current will flow in such a way that these two pair will go and make the rising edge, and after that this next this thing here, this, sorry, so this gate driver will on then, and it is giving the falling edge. So this is the basic of GPIS. Okay, so at that time we all know that power, basically this energy loss is coming from when we will find both current and voltages are there. Okay, current and voltages are there means it is giving basically the energy, because you can find V and I when at the point of any point of time, multiplication of V and I giving the corresponding power loss. Okay, if it is integrated over a time, it is giving the energy loss. Okay, so whenever this rising in and falling edge is there, due to this transistor is taking an amount of time to getting switch off and switch on, at that point of time the voltage, the corresponding voltage is becoming high. More the voltage is becoming high, current is becoming low. You may find because voltage is becoming high means it is stopped conducting. So since voltage is high means the corresponding voltage drop across this is maximum. So voltage drop is maximum means no current is flowing. So basically we are switching it off. And here you can find it is switching off slowly. Current is getting lesser slowly. And at that, in a point of time, we may find a finite amount of voltage and current, which is giving the ultimately energy loss. And energy loss means whenever it is a energy is losing. So at that point of time, what will happen? It is giving the energy loss, and then it will convert to the heat. So heat is there, and for that heat, energy loss means we are basically losing the energy in the terms of heat, not in terms of giving power to the circuit. So this DC power, whatever we are giving, so basically battery is discharging very fast. So what is the thing? Number one, heat is generated. Heat is a big problem in a circuit, and heat is not only big problem for the circuit, but also it is decreasing the corresponding battery charge very fast. So what will happen, that the battery will discharge fast, so we have to keep the battery in charging again in faster time. So that's why it's told that how we will get rid of this action is problem. So thing is that then what we'll do, we have the problem, we can get rid of this problem. Now it is coming the electronics part. Why I am giving chose this multidisciplinary field? Because I think lots of faculties are there who are there from electrical background, those few are from electronics background, few are from communication background, and few are from the computer science background. So this multidisciplinary will give you a kind of idea that you may choose in later on, that you can choose any field. Basically, now all the research work became multidisciplinary. So I have the collaborators, those who are in electrical department, so they are doing the power electronics thing. Those who are from the communication, they are doing the communication, emitting the ultrasonic frequency and giving the corresponding power. Those who are doing the embedded system thing, basically those computer science, so those they are basically making the system smarter. So, and the circuit people, they have the corresponding thing, whatever I'm trying to explain over here. So those who are the electronics part, so you can find that basically this MOSFET is a combination of a huge amount of parasitic capacitances. What is capacitance? If I am telling, this is a capacitance. What is capacitance? We know already that, okay, fine, if there is two metal plate inside, there is an insulator that create the capacitance. But if we can see that we, the human being, all these systems are basically sitting, we are sitting inside a capacitor itself. Because the ionosphere is the charge storage, and ground is a reservoir of electron. In between, there is a air, the insulator. So we are basically inside one capacitor, one big capacitor. And whenever this is come in the VLSI, in VLSI, the insulator is silicon dioxide. The metal and the semiconductor, they are basically acting as the metal plates, that is the conducting plates, and silicon dioxide, the insulator. So wherever the insulator is there and two metal or semiconductors are there, that is creating the capacitor. I told you in the previous slide that basically whenever this voltage is getting slower, we all read the transient analysis. We all know about the transient. So basically the corresponding time for charging and discharging, which is time to get switch on and switch off, that depends on the RC value. So where is C is coming? C is coming from these parasitic capacitances of the MOSFET. Okay, so basically you can find that if we can anyhow decrease the capacitance or make something to make it higher in charging and discharging, basically switching off and on, so we can do this thing. So I am telling that T on is nothing but whenever the time, by that time the MOSFET getting switched on, that depends on QG, the charge, and the I average. So you can see this is the MOSFET. The MOSFET means is a combination of source, drain, the electrodes are there, and here you can find the all the part that is not connected, that this gray section, they are nothing but the silicon dioxide. So wherever this metal and semiconductor and metal and conductors are, and this another metal gates are there, they are creating the huge amount of capacitances that is basically increasing the transient time. So what we can do? So we can do something so that the corresponding MOSFET will get some less amount of time to make it switch on and off. And another thing, we can make it in such a way whenever the heat is started generating, then we can control the speed of the gate driver, that making it little bit slower, that is a pulse width whatever we are giving in the MOSFET to switching on and off. We will make the corresponding, try to get the MOSFET stop for a time being so that it can get some time to dissipate heat, and we will continue this operation till the heat is becoming lesser. So this is the corresponding solution. So it's kind of jugaad, you know. So thing is that since the whenever you are decreasing the size, the capacitance and everything will definitely increase. Now it's coming to the circuit designer who are doing the circuit design. They are basically trying to do in a different way, that to make the whenever heat is generated, then slow the process, make the MOSFET come into the little bit rest point. So at that time, when the T1 time becomes small, so you can find the T1 time we are making smaller mean. So thing is that basically the MOSFET is getting switched on for less amount of time. So the heat, basically our on time, is basically increasing at that point of time, and we are giving the MOSFET a particular time to dissipate the heat. And here you can find the PWM. Now the computer science people's things are coming. The control logic and PWM, that is coming. So now to make this, we told that this already we have shown it. That is the PWM things. What we will do, that the PWM is the pulse width modulation, that is the changing the width of the corresponding system's pulse. So there is a control logic. So control logic, what it will do? It will do, just a minute, it will do the things that it will change the corresponding pulse width depending upon the MOSFET's situation. Okay, so MOSFET situation will, MOSFET on time will be getting lesser whenever the it will find the heat is generated. So thing is that this PWM is controlled, this control logic and PWM, it is basically coming in the how we are designing the control, this control logic. Here we will be using the control points, that's basically the CPU part. CPU part is nothing but we are telling this is the program part. There is some combination and logics are there. There is some control unit state are there, and the sequential part of there. This control logic, which is responsible for making the PWM, you can find total circuit system. Now the thing is that I told you that heat, okay, this heat need to be sensed first. Means this heat is basically generated. So when it will start getting little bit heat, you have to sense the heat. Here the sensor part is coming. So whenever we will get the heat, means there is a temperature sensor is required. The temperature sensor is basically getting the when the heat is being generated. The temperature sensor sense the heat and it will give the feedback to the control logic. So control logic and the heat sensor means itself MOS. We can use a MOS for the heat sensor. That is a completely different work itself. Any kind of time, if we say that this is a completely MOS sensor based part, MEMS sensors are there. So it will check that whether this MOSFET are getting heated and it will send the signal to the control logic. In this control logic, we will find that we will tell that how much T1 time we need to modulate. So T1 time is the smaller, how small every program will be written and interfaced with the circuit. So for that, you can find that for this micro program part, timing and everything, we are basically using the Xilinx. The Xilinx means basically that is the semi-custom design. Semi-custom design means we are giving the basically the program that may be VSDL or Verilog. We are combining the corresponding logic to make the corresponding pulse width smaller or lesser. Depending upon this program, the corresponding control unit will be built. And here we are using the Xilinx. Next, combinational logic circuit. That is the full custom design. Full custom design where we are doing the combinational logic. Basically, the combinational logic may be prepared with Xilinx, with the semi-custom design, or if you want your customized thing. So customized and semi-custom, if I tell about this custom and semi-custom design, the corresponding example of I tell about is what is the custom and semi-custom. Custom and semi-custom means whenever we are buying a flat in a particular complex or anywhere, so they are giving a flat which is already there made with their blueprint and there's their corresponding design. But inside you can make it according to your choice. So this is not fully customized. They are giving something. Now you can custom design it in a custom way. That's basically in your inside. So that became semi-custom. But whenever you are buying a plot and making a system means everything, whatever you are designing, that will be done according to you. So from the very base to the roof, everything is customized. So you can prepare everything by your design. So here, whenever you are using Xilinx, basically we are giving the program. This program is being synthesized with the standard cell library. Standard cell library means for particular logic, they are preparing their own logic system. We even don't know how this logic system will work. The logic system is used to work according to this corresponding standard library. You will just get the output. Simple, you are giving the program and getting the output inside all this MOSFET and everything is designed. But for combination logic circuit, whenever we are preparing the circuit, each and every MOSFET dimension you can change. You can make the customized design because if you think you need a very faster circuit, you just increasing the width of the MOSFET, making the R-on very less. So gradually the faster CMOS will be prepared. So that can be done with the help of full custom design. So in Cadence, we are basically using this, making this full custom design. Then just I will move to a smaller thing. I think most of you already know this, but this is the thing that I will start with inverter. The inverter means whenever we are seeing, since few people may be new to the VLSI field, That's why I will just tell the corresponding thing like from very smaller to little bit higher section. So here we all know the inverter thing, right? You are giving the 0 and getting the 1 and 1, giving the 0 and getting the 1. This is the corresponding symbol of the inverter. But is that the symbol or what is there inside? In CMOS technology, basically this inverter is built with the MOSFETs. So MOSFET means there is a two type of MOSFETs are there. One is the PMOS, one is the NMOS. That's why this VLSI, basically this is called CMOS VLSI. This MOS, they are complementary in nature. So in PMOS basically getting switched off, switched on with the negative voltage, mostly 0.7 volt for the 180 nanometer technology. Maybe the 0.7 volt is the switch on voltage. And here, when it is the NMOS is plus 0.7, it is the switch on voltage. So thing is that when this PMOS and NMOS are building one circuit, we are telling this is the CMOS technology. So both their nature is complementary. So with the help of this PMOS, this CMOS technology, all the most of the till date innovation in the VLSI, basically they are using the CMOS technology. The CMOS technology means this PMOS and NMOS, all the gates like NAND gate, NOR gate, XOR gate, and everything has been built with the help of this CMOS technology. I'm just not getting inside the design point of view. I'll just tell, okay, fine, this one is the VLSI thing. So now, the thing is that you can find this is the corresponding fabrication lab with whichever you have. We with our student went to Hiroshima University. This is their VLSI lab, and we have just entered from very material science research to the communication research. They are working for the 7G communication. Okay, so there here just I want to share my few previous experience. There the thing is that one single how we can think of one single laboratory or any kind of research system will be. So thing is that, and we also visited the Micron Hiroshima. This is the inside Micron Hiroshima thing. I will tell you few things about. So thing is that one single laboratory, how it is compromising. The compromising on which things? Number one, they are first preparing the material. Material like here power for the power electronics transistor, they are preparing the silicon carbide. After preparation of the silicon carbide, they are making the substrate. They are basically making the lithography. With the lithography, they are basically creating the corresponding substrate and creating the transistor on top of that substrate. Then they are basically doing the fabrication of the total circuit. There, the corresponding lithography they told like they are using the 100 class. They are using the 100 class nanometer, 100 class 100 fabrication house. And after that, they are testing that one. That called the VLSI testing lab. So after fabrication, they are doing the testing. After testing, they are implementing that thing in the 7G communication. So basically the work is done on 7G communication, but they have started from the building the material. So what I told, like we visited that Micron Hiroshima, and here I just wanted that corresponding. You can see whatever I told that this one is the silicon wafer. On top of that wafer, the corresponding chips are there. they have been populated over here. So these chips are basically one single chips having around billion of transistors. So you can find in this small wafer how many transistors are there. And if we are going inside the fabrication house, we have seen like that mostly here, those who are working, they are mostly chemical engineers and the computer science engineer. The computer science engineer, then you may find here the people are there. Most of the people, like they are either chemical engineer, material engineer, or they are computer science engineer. Basically, they are working in the fabrication house. Now, why the chemical we find, okay, fine, the silicon dioxide fabrication and all these things, then the chemical engineers are there, material engineers are there. But why the computer science engineer? Now, if we try to understand, here it might not be very much visible. You can see here that basically, whenever we are somebody, some fabrication house is preparing this silicon wafer and fabricating this, so there is a number of steps. Number of steps means basically whenever we are cooking, I'm telling you with just giving the example of cooking. So basically we have number of steps, right? Whenever we are creating a chicken, so basically we are first marinating it with some spices, putting it into fridge, and then we are taking it out, then switch on the gas or oven and putting it into the oven with the help of some pot, and then making the curry. Okay, so there is a different process steps are there, and you will just a to understand will be explained to understand that every single process they are doing, they have around 1 acre of area for single process. Like whenever they are doing something like lithography, whenever they are making the substrate, everything is done in a very big wing of around 1 acre area. Their building is of this area, and everywhere this after this process it is coming to the next building. So there is scheduling is required. So those who are working in the computer science, we know, and also like electronics people also know a little bit that those who learned the operating system, basically scheduling is a part. Operating systems, scheduling is the part. So thing is that this scheduling became so much important that after this process, how long it will take to move from one building to another building and move where in what kind of time, and after that where it will go. So this is a very big scheduling mechanism. Whenever near about billions of silicon wafers are fabricated in 5 minutes. So it will take 5 minutes to fabricate one silicon fiber. So thing is that for that you understand that how fast the total system is. Whenever this fast system it will be there, they are moving. So like after one wafer come, it is coming from the cutter, going to the substrate, making substrate, then the lithography, then the etching, and everything. This process steps are going on. Then the scheduling became very crucial. So Mona Sensei, who is there, you can find he is the scheduling engineer lead. He has completed his PhD from MIT. So he is telling that it is the most critical scheduling, whatever he has done in various companies. The fabrication, how the scheduling is the toughest thing to achieve. And everything will be very much automated. So you can understand the VLSI is not about to only for the electrical, electronics, chemical, physical, material engineers. It is similarly the computer science people will contribute, and they are now incorporating AI to make this thing more precise. Okay, so you can understand now. I told you that how this silicon that's corresponding this wafers has been tested and circuit has been tested. So you can find these are small, this corresponding circuits is there. So you can just see I have also taken this picture from a lens. So thing is that you can find these are the corresponding probes. Basically, you can't see these probes, these robotic hand probes are there. You can see this probe without a lens. So whenever we require to do the test, this probe is there, which is getting the voltage, current, power, that is measuring what is the experimental value is getting from these probes. They are giving the values through the system. The current and voltage is given there, and the corresponding output we are getting. So thing is that now I told that inverter design, I have already told of this inverter design. So inverter design means I told this was the inverter. Again, this is abstraction. This is the PMOS, this is NMOS. Okay, this we are doing as a circuit engineer, we are doing the same. But in original case, if you are giving, so now thing is that V1 means if we are giving the corresponding 0 volt, that became that basically making this 0 volt means here the 0 volt is given, and you can see the negative voltage has been incorporated as VGS. So here is the source, VDD is the source, and then so it is giving 0 means basically it is getting minus VDD, that is minus 5 volt, and this PMOS is on. When this PMOS is on, it is flowing this current through this corresponding MOSFET, and it is giving the 1. So when logic 0 is given in output, we are getting logic 1. Similarly, when the logic 1 is given, when the logic 1 is given over here, so V in is 5 volt. This is the source of Mn. So whenever this 5 volt is there, the 5 volt is already been given in the VGS of this NMOS. So it is logic 1. So this NMOS, whenever this NMOS is activated, it is giving the direct path to ground, making this V out as 0. That is, there's this V out as the 0. So whenever we are giving logic 1, this is become logic 0. This is the basically inverters thing. I think so. This is the corresponding circuit. Now I will discuss. Okay, fine. This is the corresponding thing. We learned that, but we want to design that inverter. I told you that with Cadence we can do the full custom design. Means this all this MOSFET I can design individual MOSFET. I cannot design. I change the corresponding dimension of the individual MOSFET, and we can perform how fast this MOSFET will. So now I will tell is that experimental and the difference between and sync with the experimental and simulation. Now we all are doing simulation, but let me ask this thing that what is simulation? What is simulation we are doing? So can anybody from audience can tell me that what is basically simulation? Because every individual faculties who are here, I think they have done the simulation task. Basically in India, simulation is the most important, most promising field where people are doing. But I just wanted to ask, what is the simulation do you want? If you feel that okay, we are doing the simulation, what is exactly that is? Anyone can answer? What is the simulation? What we are doing the simulation? The experimental thing we done, okay, fine. With the breadboard, we are making the circuit, we are making this thing and getting the corresponding output in CRO, DSO, and everything. So what is simulation we are doing? What is this simulation is? Okay, fine. So if so, I am pretending the most of the people they do have done simulation. So what is if we want to design that inverter? So for this inverter or for any circuit, we are basically dragging this from if it is a cadence. So we have done already spice. Basically, cadence is a better version of spice. Basically, that is spice itself. So we are incorporating one MOSFET. This MOSFET, it is nothing but a program. The symbol has been created inside a program or function. Rather better to say this is a function. The function of this MOSFET is basically running. Okay. So whenever we are dragging this MOSFET in your cadence platform, basically one program, the function started doing. Then what is this program? This program, I just want you to know that what is this MOSFET program is. Okay. So just to give the corresponding idea of this MOSFET, I'm just giving one small thing to you. Even if we are making this MOSFET told this, but in original fabrication, you can see this is the fabricated inverter. PMOS, NMOS, this is the gate, these are the VDD. This will not like this previous symbols. You can see this is the corresponding symbol. Here this gate, drain, and all these things are there. Here you can find, you have to find this, where is the gate and where is the drain. And that is basically one kind of, you can find like previously in our, whenever we are doing in class 1 or 2, we are preparing the thing with the mud. Basically the pottery and everything we are doing. This is like just pottery. They are preparing, basically this is the silicon wafer. On top of that, various kind of lithography and every task has been done and they have created this kind of thing. So this is completely different what we have done here or here, right? So we are thinking this is the inverter. Then we are thinking, okay, this is the inverter. But in original case, we find in the fabrication, this is the inverter. And this is the corresponding nanowires. This is the wires. We are find like this one is the wire, this one is the wire, maybe this one is the wire, maybe these are the wires. But in original fabrication, this kind of wire has been designed. Then what is the purpose of this simulation? Means we are basically creating this, but originally this. In fabrication, we are this kind of thing is designed. What you can see, this is the NMOS. Now I will like to say you one thing. This NMOS has been fabricated in the fabrication lab first. To make a clear idea about the fabrication, I will just make you know that what is basically happening. Basically, this is the corresponding NMOS they are fabricating. After that, how I told that in this way, they are checking the VI characteristics of the MOSFET. Okay, they are getting different kind of VI characteristics like just I am telling you. So this is the corresponding output characteristics they are getting for NMOS. This is the VDS. This is the corresponding ID, and they are getting the corresponding characteristics for different VDS. They are getting different IDs. Okay, so that's how they are giving us various kind of GM thing, GDS, various characteristics. So whatever I have done in the HISEM Research Center, basically we used to model the MOSFET. Now, what is the modeling of the MOSFET? Then I can tell you this. So with these VI characteristics, basically we got these various kind of characteristics. Okay. Now I told you that whenever we are doing something in spice, this kind of MOSFET we are basically putting. This is nothing but a function is running. This is nothing but a function. Okay, this is the function of NMOS. Okay, so this is the function of NMOS means I have to make a program of NMOS where I can get my output will be this kind of characteristics. VD versus ID, VDS versus IDS. Okay, and I will get this kind of characteristics. Okay, so I'm just giving you only this output characteristics. We have to make GM, GDS, and transfer characteristics, GDS2, GDS3, GM1, GM2, GDS2, DS3 means basically the differentiation of GDS, differentiation of second order differentiation of GDS, GDS2, 3, these are. So whenever we got things from the experimental fabrication house, this one is the ID versus VD, and we got the corresponding characteristics in our program from my NMOS function. Now this is my program, this is the experimental result. So then we used to lay it in a single. So there it becomes this dotted at the experimental, and this is my program. So now we are using ICCAP. There is a software called ICCAP. Then we are changing various characteristics like mobility, like velocity saturation, and lots of parameters are there in my function, this NMOS function. We are changing these parameters to fit with the experimental result. Then we can say that now the simulation model of the MOSFET, of this MOSFET, let's say this NMOS, is done. So this corresponding MOSFET, we have got some kind of experimental values. My function was giving one single characteristics, and with the help of ICCAP and this parameter shifting, I am telling it in a general way, but this is the toughest task, to basically fit one single model with this parameter. It takes around 3 months with complete efficiency. Okay, so this kind of thing is done when all the characteristics like GM, GDS, output characteristics, and the transfer characteristics, when all the characteristics are similar to the experimental result and my program, then I can tell this MOS and this MOS is same. So this MOS is now dummy of this MOS. Just like previously, those who worked in 2000 before 2015 or something. So then we are using in the desktop, there is a keyboard. Whenever our keyboard was not functioning, we used to use the virtual keyboard. Previously, it was the hardware keyboard. When we are pressing A, basically whenever we are pressing A with our finger, A is displayed. When we are pressing X, X is displayed. But in the virtual, whenever we are basically running the virtual keyboard, that is the simulation of the original keyboard. The simulation of original keyboard means that is a model of original keyboard. Original keyboard, if in the virtual keyboard I press A is displayed. If I press X, X is displayed. So whatever we were doing in the original keyboard, if I can do the similar thing, the similar performance I will get in the virtual keyboard, then I tell that, okay, fine, this program is running exactly as the physical keyboard was running. So that is the very good model of the original keyboard. Similarly, this NMOS is there. This NMOS is fabricated. They has generated this experimental result. Then my program is got this kind of result. Then I fitted my result, my program to the experimental value. Now I can say this MOS and my MOS is basically same clone or dummy of the original fabricated MOS. Similarly, we used to model this PMOS, we used to model this nanoware, everything we used to model and put it, give it to the cadence. Here, I just want to give you one more information. In general, whenever we learn the VLSI or any microelectronics, we tell that, okay, fine, ID is equal to mu Cox by 2, blah, blah, blah. So these equations we used to use. And we tell for this, if the mu is this, width is this, L is this, then if we give the VDS and VGS, this kind of current will flow. But unfortunately, if this MOSFET is built by TSMC fabrication lab, if this similar MOSFET is prepared by Intel, if this similar MOS is prepared by, let's, Global Foundry or Samsung, every individual MOS's performance are different. All the MOSFET that is prepared in different fabrication house, they are completely different. So if I am preparing one single function, it will not cover TSMC, Intel, GA for Samsung. They are giving different experimental output. And that's why all the MOSFET, my clone function will be different for TSMC, Intel, Global Foundry, Samsung, everyone. And I have to feed this model with the experimental result with IC cap for all these foundry. That's why each and every foundries, this kind of all these devices they used to produce, they used to create one single thing that is called PDK. in this PDK, so you will find TSMC PDK, Intel PDK, Global Foundry PDK, Samsung PDK, our SCL PDK, our UMC PDK, all this PDK you will find, because everywhere the corresponding MOSFETs model or interconnects model they are giving, they are different. That's why for whenever we are designing this kind of MOSFET in the cadence, then we have to incorporate the corresponding PDK or call the PDK in the cadence. So those who done a little bit in cadence, they can find whenever we start creating one library, we have to incorporate that which kind of PDK we are using. Then only we can start designing this MOSFET. That's why I told the model and this fabrication's result should be similar, because now this NMOS and PMOS in a particular circuit, it will be billion and billion of transistors. So billion and billion MOS model, MOS functions is to be called, and they are running simultaneously. Basically, your program having billion number of function calls, and they are working simultaneously to prepare to build one circuit that I have told you here, that for let's this one, this is a control unit. Here the control unit and CPU lead the combinational logic circuits. They are basically we have done to cadence virtuoso. This corresponding circuit is prepared. So you can find that, okay, fine, this is the thing. So now we have done it till the circuit design. So this circuit design is done. This circuit design is done. Now this is the very preliminary part to see the what is the output will be. Now the next part is coming, the layout design. The layout design means I would like to say, give you one more idea. The thing is that whatever this, if it is a MOSFET, the MOSFET is giving, this is the N plus, this is the N plus region, and this one is the gate. Now in the CAD, basically this is the cadence. So this is the CAD design. So if the every individual CAD is designed with the elevation. So if we want to see this kind of MOSFET from the elevation, how it will look? This one is look like this. This one is will be look like this, and this N will look like this. So elevation part. So this is a kind of one diffusion or MOS, one diffusional MOS. Basically, this is the complete MOSFET, and this is the metal contact. Metal contact means here is the metal contact is there. Here is the metal contact is there. This one is metal contact. This is the diffusion. This is the N plus. This is the corresponding N plus, and this is the corresponding silicon dioxide, and this is the gate part. So this is built with the polysilicon. So this is the corresponding polysilicon. This. Now this layout is prepared. You can see here. So here also you can find this is the corresponding NMOS thing, and here you can find the corresponding gate is, you can see here after my thing. So you can see this is the corresponding MOSFET. This is the N plus. This is the 3D. So this is the N plus. You can see here N plus. This is the corresponding N. Sorry, this is the corresponding N. This is the corresponding N plus. This is the gate. So I have seen it here. Here. Okay. So this is the corresponding top view you can find. The 3D to 2D to the layout. So this is the part when we do the circuit design, then we will do the layout design, Okay, and finally this one is the fabrication. So this is the design. But whatever I told, that this design will be built as this MOSFET, the function is written or modeling has been done for this MOSFET. This is called compact modeling. Whatever I just discussed few minutes earlier. So this compact modeling, basically this I told you this is the compact modeling. The compact modeling, the MOSFETs program is looked like this. And generally, this language we are using, that is called Verilog AMS. VAMS. That is called Verilog AMS. Okay. So this Verilog AMS are, this program is done here. This is the corresponding. This is a small program I told, but this is that not small. There's a various kind of abstraction, various kind of more big, complicated things. So to make you understand, make a kind of give some idea about the compact modeling, I have written this small program, like where basically we are using like parameter like VTH. Mu means the mobility of the transistor, that is the COX, that is the W, and that is the L. And you can, if I will tell in HISIM, whenever we are doing basically writing this compact modeling, we had a team of a bunch of various multidisciplinary people. One person who was there, those who is coming from the physics background, basically he used to do the basically material science part. One person who was the chemical engineer, who used to do the corresponding console part. Basically he is doing, used to get the corresponding chemical atomic section, quantum section. He used to do, he used to check. We had that we basically electronic people, we used to do the corresponding circuit part, and the for that any particular circuit, how this VTH, mu, COX, all this will be affected. Accordingly, we used to write the program. And one person was there who didn't know, he didn't know about this physics, about this mechanics, about this chemical thing. He only knows the program. He is from completely program point of program. There is a computer science background, and he used to write and make the program very efficient so that it can take lesser variable, higher speed. That the main purpose of him was to make the program, make the model smooth running and run with lesser amount of time. So you can find that how many people are working in the VLSI industry itself in the compact modeling section. So now you can say that to write this compact model, we have taken this corresponding value like VTH, mu, COX, W, and L. I told you already that all are different for different fabrication house. This I can see this is the
Hello, sir. You are not audible. Hello. 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 Hello.
Yes, sir, you are audible.
এই আমারটা শোনা যাচ্ছে না কেন বলুন তো? হ্যাঁ,
You are audible. You are audible, sir.
হ্যালো, হ্যালো। I'm not hearing the presentation. কি হচ্ছে বলতো? একটু একটা হচ্ছে। হ্যাঁ, হ্যাঁ।
Hello. There is a technical issue. Speaker sir has been disconnected. So just wait for a while. You will join soon. So just wait.
Sorry for the interrupts. Please ask to make it turn on. My sharing is, yeah. Can anyone let me know that how, where I have just stopped? Means my
হ্যাঁ?
network got disconnected. I'm not getting. Up till here, it's been done.
Yes, yes. You continue, please.
No, no.
Please continue, continue.
Where
Please
my
continue.
network got disconnected? I didn't know that when the network got disconnected.
Please continue, sir.
This one.
Yes, yes.
Yes,
Previous.
yes.
Okay. So I already told you that. Okay, fine. Just a minute. So this compact modeling section, I told already started telling you about the compact modeling. Here you can find that corresponding all these compact models I told you that has been done in Verilog AMS. Okay. So in Verilog AMS, you can find to design this MOSFET. Basically, this VTH, this mu, this capacitance, COX, all these things are there with which these are all parameters of the MOSFET. They are different for different TSMC, UMC, Intel, SCL, all the fabrication lab. Basically, they are having the complete different parameters. So that's why we have to make the corresponding program, like I told you about the IC cap. I will come next also, that I have to feed the parameters. Now, I told you that before going to the parameter extraction or parameter fitting part, I will just tell you one more section of the VLSI design. That is called the device design, that is done with TCAD. There is two kind of TCAD is mostly available. People are basically working with the the corresponding third-party TCAD also, that is the open TCAD. But that basically Synopsys and Silvaco, they are making the TCAD. TCAD means this MOSFET we are preparing the program. Here, this MOSFET are designed by the device engineers, where I can tell that what will be the doping, what will be the exact material of the corresponding MOSFET device. Okay, so this TCAD is another section of the device design. So this is also a very big section where the people working in the industry, and just to make you understand, so that although this is FDP, but you can motivate your student, just like telling that Global Foundry, I'm my collaborator. I used to go there and also used to like teach them few things. So thing is that, and we also get a kind of information sharing and everything we used to do. So mostly this TCAD engineer starting salary is coming around 1.8 lakhs per month. And if you are PhD, then this TCAD engineer is getting more than 2 lakh, 2.2 lakhs. So best TCAD engineers is doing. The ICCAP people, most of the ICCAP people are working in different PDKs like Intel, like this Global Foundry, and where their starting salary is from 2.5. So I told you to make one single experimental value to the corresponding the run that program's value, outcome value, that will be just be similar and fitted well, so that you can say this is the very good model is prepared. And their starting salary for the masters is 2. And those, if you are the PhD and you have experience, their salary is starting from 2.5 lakh per annum. So you can motivate your students, like also you people may start working and give the corresponding thing, so that it will be just like what mostly India's mind is mostly concentrated in the software. But in both, again, I told that what the India's point of views are coming, the semiconductor industry is going. So the things, the high salary thing will come, and we should be prepared like this, so that our student can get the opportunity to work in the semiconductor and VLSI field. Okay, just moving forward. So then this ICCAP I have already mentioned. This is the ICCAP parameter extraction we used to do with the experimental value to our simulation value. Then only a very big concrete model is prepared. Now I will give to end up with the total solution approach of the VLSI section, that I told you that we have started with to build one single power MOSFET. The power MOSFET was there, that was required to get the less heat. To get the less heat, we told the simulation of the trench MOSFET, whatever we have discussed in that, to get the ultrasonic frequency. The simulation means we are doing with the cadence. Now, this has two parts. One part is device design based optimization, and another part was modeling. Device design based optimization, mostly device design has two sections. One is the material section, and one is the device design section I told TCAD. Mostly this material section has been done by physics. Also in engineering, few people are doing that in the material section. The TCAD section also, mostly the mechanical people, they are doing. Also like our electronics people, they are doing this TCAD section. And this modeling. For this modeling, I told you, this all kind of people are required to get the modeling part. So modeling section means here we are preparing the very good model, very good replica, very good clone of the MOSFET, which will run in the SPICE environment. Okay. So now this simulation will be done. So this device, this compact model finally come to simulation, that is the simulation environment like Cadence, Mentor Graphics, Synopsys, they have all the spice environment part. Okay, now the thing is that this is the corresponding approach. Now this is given to the circuit people, circuit as well as the computer science people. Thing is that here the GPIS circuit based solutions are there, and another one is that simulation that to write the program with the control logic. Control logic means maybe it is the A of full custom and semi custom. Here computer science and the electronic people will do their job. And finally, we move towards the tape out after doing the layout and post layout simulation. Okay, so and the also self-fitting characterization part that mostly done by the physical and electronics people. So after tape out, we test the system and incorporate this thing in the swarm drone and interfaced with the swarm drone to emit the ultrasonic frequency. So thing is that the compact model to PDK to circuit simulation, this thing is done. And now I will go more towards final characterization of the cell bit section. So this is the corresponding section where the circuit level thing we are doing. Mostly previously was a kind of mostly fabrication modeling at this thing. And then we are going towards the switch loss simulation, consider the cell fit. Without consider cell fit, we are basically getting the switching loss. Then simulation of the power electronic circuit that we do in the Cadence. And also this thing, we the self fitting, the IDS, VDS, all these things we used to take through the corresponding this temperature sensor, and gradually the MOSFET simulation is done, and finally the circuit is prepared for the solution. So this is the corresponding complete thing which will start from the very application like drone based one signal emitting circuit. From signal emitting circuit, you are basically designing various sections, circuits. To make the circuit, you require the, since this is the smaller thing, so you require the, you can't just do it in the breadboard or something. Basically, there is a smaller MOSFET. So you used to do the simulation. Simulation is done in the Cadence. In Cadence, the MOSFET, how the MOSFET's program is done, that is to compact modeling. For compact modeling, we require the device design section for, and as well as the fabrication section. This fabrication section and all these things giving you the basically experimental result. Then we fit with the IC cap, give this corresponding model to all the fabrication house. They used to make the PDK, give it to the Cadence. Cadence people used to design the circuit, make the layout, fabricate the corresponding circuit, and we incorporate that circuit in the swarm drone and emit the frequency. That's it. Thank you very much. And now I am open for your questions.
Any questions from participants? Any questions?
And also, if you have any kind of questions coming in your mind, you just want a kind of different, maybe we can discuss. You can come up in this my email ID. You can approach me, and few possible collaborations could be done in future.
Thank you very much, sir.
Thank you
For your introduction. I hope this session will be very helpful for all the participants. Thank you very much again, sir. Now I am sharing your digital memento for this session. Is it visible, sir?
Yeah. Anybody
Uh,
any kind of
Please kindly accept this
suggestion or
digital memento, sir.
something? Thank you, Suresh. Yeah, feedback link. It is common. Oh, nice. Thank you. Thank you very much.
Thank
This
you,
is your
sir.
thank you all the participants and thank you, sir. This is
Yeah.
your digital memento. Kindly accept this memento.
Thanks a lot.
Okay. Thank you, sir. This session is very informative session, and I hope this session will be very helpful for all the participants.
Yeah, thing is that if people start doing or getting kind of few things, I have already given a very big domain. If people are interested to work in future, that will be the success of my uh, this talk. And also, if I find people are basically finding this thing and more students are working in this field, then I'll feel very happy. Thank you.
Okay, thank you, sir. Thank you all the participants again. Good afternoon, all the participants, and again, thank you, sir, and good afternoon, sir. Now, I am ending the session.
So I'm leaving.
Okay, sir.
Okay.
Okay, sir. Hmm?